Hello, my name's Tim. I'm the programmer for Koala Natural English Programming Language. And if you don't know what that is, that's a programming language for Windows that allows you to be able to just type in instructions in plain English, have the computer interpret it, and run those instructions. So I have the editor in front of me. Let's get started. I've got a simple program that will just open up. We'll go through it, step through it line by line, see exactly what it's doing, and hopefully it'll work. So let's give it a go. The program that I've written is just a basic program for calculating prime numbers, and I have the code in front of me right here. I say code, it's not really code, it's just English. But if we go through and execute this, we will hopefully get a list of prime numbers that comes out. So let's step through it line by line, and I'll go through exactly what's happening. In the editor, we've got these 4 buttons currently. The main 2 ones that you need to know about are this one and this one. Key difference being is that one of these buttons will just run the code as is, and the other one will actually debug it line by line. So what we want to do here for the purposes of demonstration is debug this code, and we'll press that button. So already the code's been compiled. It's ready to execute the first instruction.
Do you hear that?
And if you're wondering why that first instruction is line 13 right in the middle, there's a good reason for that. That's actually the first instruction that it encountered, which was not part of a definition. And in this case, we've got these lines up the top, which define a function up here. The function definition being is this number that we're going to feed into a prime number. And subsequently, we have all of the instructions associated with that function. So the compiler knows that this is a function. It knows that it's not the place to start, but it's rather the place where, if it's called later on, it can enter it, and it will. So the first instruction we've encountered is this set max int equal to 10,000. And set max int equal to 10,000. What that's going to do is it's going to create a variable. It's going to automatically interpret that as an integer, and it's going to assign that value to that variable. So we step on that. We can see on the right we've got our list of variables in memory. Currently we have 2 functions, one being the main function, the other being the user-defined is number prime function, and we've got this variable here which is max int, which we just defined in the instruction above. So the next instruction, set n equal to 2, you step over that and it'll do the exact same thing, but now we've got this variable n and it's equal to 2. The reason that we're starting at 2 here is because 2 is the smallest number to check for in terms of divisibility or candidacy for primality. That's math. What that means is that any number can be divided by itself and 1, so we're not interested in those numbers. What we're interested in is the numbers outside of those numbers, and the first number outside of 1 is 2, which is why we're starting at number 2. And we've got this next instruction here, which is while n is less than max int, right, do the following. So at this point we know that n is 2, we know that max int is 10,000 as we've defined it above. What this is going to do is it's going to do for the range, for the number of iterations between 2 and 10,000, it's going to perform the subsequent lines of code. And we step into that, we'll see exactly that it starts doing that. So now we perform the function that we defined earlier called isNumberPrime. Okay, so if I step into this instruction, what we expect to see is that this code, this head for the execution is going to end up over here inside of this function. since this instruction is telling us to go to that function and run it. So let's see where that ends up. We're inside the function now, and it's saying we want another variable, and we're going to set this equal to 2. And how this is different from n, which we've just defined, I'll explain in a second. So we're going to do that. We've now got x, we've got n, we've got max int. We've got a lot of variables, but not much has happened. But now we encounter this other loop here, right? So it's while x is less than n. Okay, well, in this case, n is the number that we're checking for primality. X is some variable that we've just defined, and max int is the number that we want to check up to. So we don't want n to exceed 10,000. So x in this case is going to be the divisor that we're going to check to see whether or not divides n equally into equal parts. So if I step into okay, so while x is less than n, it's gone and evaluated that condition. It's determined that x is 2 and 2 is not less than 2, so we're going to return the answer as yes. That means that 2 is divisible by only itself and 1, therefore it's prime, right? 2 is a little bit of an annoying number to work with in terms of prime numbers, because it's the only even prime number, and it's also the first prime number that we encounter. So bear with me. What we're going to do is we store that as number is prime, right? So we've noticed that this function here actually told us that the answer is yes. Now we encounter this store this as number is prime function, which what store this instruction does is it takes whatever the preceding line was and it stores it as a variable in a way similar to set n equal to 2 does. It does the same thing, it just is implied that you're talking about the preceding line. So if I execute that, now we should have number is prime, and it should be set to yes, in this case true. Yes and true and 1 in a Boolean data type, all the same thing. So now we've got this condition here, which is if number is prime, which we know it is, what we're going to do is we're going to write it out to the console so that we can see it. And if I step over that, we see that that's exactly what it does. So we've got 2 listed out there. Set n equal to n plus 1. Another way of saying that is just increment n by 1 and go to the next number. So 2 becomes 3, 3 becomes 4, 4 becomes 5, and so on. So step into that, and we look over here. Now n is 3, and we're ready to do the loop again. So now the state that we're in is different every time we execute this function is number prime, and we can expect that this function is number prime will be called from between 2 to 10,000 times, right? In other words, we're going to generate, or we're going to check the numbers between 2 and 10,000 and find out if they're prime. So step into that again. We will step over. So again, we're starting at 2 because that's the smallest divisor that we can start at to check primality, and do the whole thing again. The path in which it's going to take now is different to the path that it took last time, because last time it bailed out here and it said, well, x is not less than n, so I'm just going to return the answer yes. This time x is actually less than n. If we look over here, x is 2, n is 3. What we can expect is it to go into this loop at least one time. So if n divided by x is an integer, what does that mean? N is the number that we're checking, x is the number that we started with, and we will further down be incrementing as well. So now what we want to do is we want to check all numbers less than 3 and above 1 to see whether or not it divides 3 equally into equal parts. And the way that we determine that is if n divided by x is an integer. In other words, is it a whole number, or is it like a decimal? if it's a decimal, we don't need to worry about it, because it doesn't divide n equally, therefore it's not a prime factor of n. So if we step into this, it determines that n divided by x is not an integer, and if I do that in my head, 3 divided by 2 is not an integer, it's 1.5. So what we're going to do is we're going to increment x by 1. So we encounter this instruction again, set x equal to x plus 1, and do the same thing, right? Okay, so now it's going to do the same thing. It's evaluated that now we've got 3 as x, we've got n as x is 3, n is 3, and when x is no longer less than 3, so what's happened is we've reached 3 without finding a divisor we've reached 3 without finding a divisor less than 3 and above 1, and what we can infer here is that the answer is yes, it is a prime number, because we've reached the end of the range of possible divisors. We didn't find an integer that divided into it equally. Therefore, we can assert that yes, 3 is prime. And actually, 3 is prime. So it's going to go and do the same thing out here. It's going to say, when we write into the console, we've got this new prime number down here, and it's called 3. Okay. And it's going to do the same thing again, right? We've got 4, and it's going to check for divisors 2 and 3 here in 4. And what we should see is that for n equal to 4 and x starting at 2, we expect 4 divided by 2 to be an integer, because 4 divided by 2 is 2. In which case, what we're going to do is we're going to return the answer as no immediately. We're going to say that no, this number is not prime because 4 is divided by 2 equally. And surely enough, that's correct. 4 is not a prime number. So I think that sort of basically highlights how the logic works here. If I just close this and reopen it, and that's sort of the only way I can stop the execution of it at the moment. Again, this is still under development, but open this up again. I'll run this button now, and we can see that the same code that we were looking at before now executes much faster. And we get the list of prime numbers just getting spat out down the bottom here. It's bottom left. And something you might notice as well is that the list starts churning out numbers really quickly, and then it slows down, and it gets slower and slower because we're checking the first 10,000 numbers to see whether or not they're prime numbers. And there's a reason behind this. There's a reason why it gets slower and slower, and the reason is that each number that you check that is higher than the previous number takes longer to check all of the numbers beneath that number. For example, if I'm checking the number 3, well, I only need to check for a divisor of 2 to know whether or not it's prime. If I'm checking the number 10,000, I need to check the number 2 all the way up to 9,999. Or I think there's even shortcuts that you can take where you check up to half of the value of n. But irrespective, that the numbers that you need to check are much greater each time you increment the number. So you can imagine that for very large numbers, it takes a very long time to figure out whether that number is prime or not. And there's shortcuts you can take, which is looking at the last digit of the number to determine whether it's prime or not. We know that it's not going to end in an even number, like 4, 6, 8, or 2, because that would make it divisible by 2, which would ruin its prime candidacy. It's not going to end in 5, because that would 5 or 0, that would make it divisible by 5. So the only numbers that it can end in are 1, 3, 7, and 9. And surely enough, if we go back through this list, we see that all the numbers that this has produced, this program, end in 1, 3, 7, or 9. So that makes me confident that we are looking at a list of prime numbers here, 2, 3, 5, 7, etc., etc. And hopefully the logic is somewhat easy to follow along. Hopefully it makes sense. And I look forward to making more videos about the capabilities of this programming language. I think the next video I want to make is about being able to visualize this data. So perhaps taking this list of prime numbers and feeding it into another function that would then produce an image or a graphic that we could load up on the computer, and we could actually see the data in a visualized format. So thanks for watching, and hopefully I've got another video soon.